Good evening, everyone. Welcome to tutorial session of the course Principles of Organic Synthesis. This is our week 4 tutorial session, and in this session, basically, we will be seeing the week 4 tutorials, that is organometallic reagents. So basically, organometallic reagents, we can say, if in the case of a carbon and like alkyl halides, the carbon will be positively polarized and the halogen will be negatively polarized. The reason is the electronegativity difference between the carbon and the halogen. But in the case of in the case of an alkyl halide, this carbon will be more susceptible to react with the nucleophiles. But in the case of an organometallic compound, this carbon will be bonded with a metal. That means the metal will be electropositive and carbon will be having a partial negative charge that we can say as a carbanion. So this carbanion will always have a tendency to react with the electrophiles. And here what is actually happening is that a bonding pair between this carbon metal is always shifted towards the carbon. So as we can see the definition given here, the carbanion is basically an anion in which carbon has an unshared pair of electrons and bears a negative charge. And these carbanions are strong bases, and strong bases means they are extremely strong bases. That's why they will get easily quenched by very weak acids like water, alcohols, amines, carboxylic acids, amides, and even terminal alkynes. So these limitations of these carbanions, we make it as a utility to react it with various electrophiles, and there that is why this organometallic reagents are very important. So in the last lectures we have seen why this organometallic compounds are very versatile compounds and how to prepare this organomagnesium reagents, then how what are the basic reactivity of this organomagnesium reagents as well as organolithium compounds. Then these both are strong bases, strong nucleophiles, and act as and they're very sensitive to moisture also. And we have also seen that mostly when we prepare this organomagnesium reagents, we prefer THF rather than diethyl ether. This is because diethyl ether is having a Lewis acidic nature, and that can result in the formation of aggregate species of organomagnesium reagents. But in THF, there is no such possibility. That's why we are preferring THF over diethyl ether for preparation of organomagnesium compounds. Then we have seen the stereochemistry controlled by the chelation model as well as the Cram's model in the case of organomagnesium and organolithium compounds. Then, in the case of organomagnesium compound, we saw the reaction with the carbonyl compounds where the reaction can proceed either through a four-member transition state or through a six-member transition state. Yeah, that where then we have seen the reaction, the coupling reaction between using organomagnesium reagent, that is Kumada coupling, and using organolithium reagents we can do Woods coupling. So these were the basic things which we saw in the last week lectures. So here I have given how we can prepare the organolithium and Grignard reagents, that is basically by the reaction of alkyl halides with lithium or magnesium to give organolithium compounds or organomagnesium compounds respectively. So both of these are very strong nucleophiles and very strong bases. So, and in key here there is a summary of the Grignard reagent reactions, that is with the aldehydes, ketones, esters. So with esters, it adds twice. That is, double addition will take place if we use two molecules of organomagnesium bromide. And in the case of addition to epoxides, adds to least substituted carbon. And if the organomagnesium reagent is being added to carbon dioxide, we will get the carboxylic acid. Now, this Grignard reagents can also undergo reaction with water or proton to give alkenes or alkanes, we can say. So, having all these things in mind about the organolithium reagent as well as organomagnesium reagents, we will move towards some problems. We can discuss some problems regarding these topics. So, the first question is predict the major product of the following reaction. That is, here a lactone is given. So, this upon treatment with this two molecule of methyl magnesium, molecules of methyl magnesium bromide followed by hydrolysis, out of the four options given here, which will be the major product of this reaction. So I will give you some time to think about this and which will be the major product out of this. And just now, just before some time, we have already mentioned that in the case of esters, Grignard reagents can undergo double addition. That is, it can add twice. So keep that in mind and try to solve this problem. And so this is also a lactone, which is basically a cyclic ester. Okay, so here what is happening is that when the first molecule of this methyl magnesium bromide will add on to this lactone, that is this methyl, which is having a negative charge because it will be negatively polarized and this magnesium will be positively polarized. So this negatively polarized methyl group will attack first on this ketone, and what is happening first is that this ester ring will, this bond will open up, and here it will be OMGBr, and here it will be one methyl group added, and here ketone will be there. So that will be the first intermediate we are getting, that is this one. So since we are using two molecules of methyl magnesium bromide and here is one ketone, the second molecule of the methyl magnesium bromide will add upon this ketone again to follow to get this dimethyl substituted hydroxy compound, dihydroxy compound. So this is what is happening with this reaction. So first molecule of methyl magnesium bromide will add upon this ester, and this bond will be opening up to form this OMGBr here, and here this ketone will be resulting, and over this ketone the second molecule of methyl magnesium bromide will add to form this compound. So the correct answer is option D. Now moving on to the second question, the major product of the following reaction, that is here this benzene ring substituted with methyl group and nitro group over ortho position. So to this we are adding this vinyl magnesium bromide in THF at minus 40 degrees Celsius followed by hydrolysis, which will be the major product out of this four options given here. So here, as we can see, this is an example for an organomagnesium reaction of an organomagnesium reagent, and here this nitro group will be the primary reaction center of this Grignard reagent. So think on that way and try to get the product. This is actually quite a tricky reaction. We will not be able to completely understand what is happening here. Maybe I will show the answer first and then maybe you can try to get to that answer. So the correct answer is option D, that is this methyl substituted indole. So basically, what is happening here is that first this vinyl magnesium bromide will add to one of the oxygen of this nitro group, and that will result in this particular intermediate. So forget this, whatever label is there. So once this form this particular intermediate, again this oxygen lone pairs will go here, and this will leave as this vinyl O magnesium bromide. And then again whatever remaining this n double bond O, to that oxygen again the molecule of vinyl magnesium bromide will be adding to get this particular compound. So then what is happening is a basically 3 3 sigmatropic rearrangement. So if we are considering this as 1 2 3, and here 1 2 3, this 1 1 bond, that is the bond between the nitrogen and oxygen, will be breaking, and the 3 3 position new bond will be forming. That is this position and this position new bond will be forming. So we will get this particular compound as a result of 3 3 sigmatropic rearrangement. Then again what will happen is this nitrogen can attack over this aldehyde here and forming this particular intermediate. Then what will happen is that this vinyl magnesium bromide will take up this proton, and that bond will shift to here, and then this nitrogen will take, upon hydrolysis will give this NH, and upon hydrolysis this OMGBr will be OH2 plus. That is, it can leave us water molecule, and aromaticity will be retained by the removal of this proton to get this methyl substituted indole. So that is a basic mechanism for this reaction. I will explain that once again. So the first molecule of vinyl magnesium bromide will attack over this particular oxygen of this nitro group, which is not negatively polarized, and that will form this bond will shift to here, and that will form this OMGBr, this intermediate. Then what is happening is that this will leave out as this vinyl or magnesium bromide, and this bond will shift to here, and it will be forming this particular intermediate, that is N double bond O. Then the second molecule of vinyl magnesium bromide will attack over this oxygen, and that will form this intermediate. Then there is a possibility of 3 3 sigmatropic rearrangement for this compound. So it will be basically 1 2 3 1 2 1 2 3. So 3 3 bond will be forming, and 1 1 bond will be cleaving to get this particular intermediate. Then what is happening is that again this proton will come here, by this proton will be taken by this vinyl magnesium bromide, and that bond will shift to here, and this bond will shift to here, and that nitrogen will take up water molecule, and this magnesium bromide upon hydrolysis will convert into a OH2 plus, and then again this proton will shift to here, and this will leave as stable water molecule to get this methyl substituted indole as the major product. So the correct answer is option D. I hope it's clear. Now, moving to the next question, the major product formed in the reaction given below. That is, this particular chiral auxiliary attached alpha beta unsaturated ketone is there. To that, we are adding phenyl magnesium bromide. But the main thing to be noticed here is we are adding that in the presence of copper bromide dimethyl sulfide complex. So, out of the four options given here, which will be the major product? So, we can see the first two options are basically 1,4 addition product, and the last two options are basically first two are 1,4 addition product, and the last two are 1,2 addition product. And so, out of this four, which will be the major product of the reaction? So here what is basically happening is 1 for addition of this phenyl magnesium bromide, because in presence of this copper bromide dimethyl sulfide, 1 to addition will not be preferred. Moreover, 1 for addition will be more preferred. So the correct answer is, out of this four options, one from this first two will be the correct option. Now we have to see what is the exact stereochemistry of the phenyl group that is undergoing 1,4 addition over this alpha beta unsaturated ketone. So we have used here this particular chiral auxiliary to control the stereo selectivity of this incoming phenyl group. So since already this in this existing chiral auxiliary, this phenyl group is in alpha position, so it will hamper the incoming nucleophile to enter from the alpha position. So the incoming nucleophile will always be coming from the position opposite to this, whatever position is occupied by the chiral auxiliary. So the correct option will be answer option 1. That is, the incoming phenyl group will be coming from the position opposite to the existing phenyl group. So because of the presence of copper here, 1 for addition, that is Gilman addition, will be preferred over 1 to addition. So that is, phenyl group will be attacked over this position and the stereochemistry will be controlled by this particular phenyl group. It will be opposite to this phenyl group. Since this is alpha, the incoming phenyl group will be occupying the beta position. Moving to the next question, the major product formed in the reaction given below. That is, this particular compound, upon treatment with this active magnesium, then in the second step with carbon dioxide, followed by hydrolysis. Out of these four options, which will be the major product? If anyone is here, they can try to answer this question as well. Already we have seen and discussed these questions in the week 4 lecture videos. So here the correct answer is option C. That is, this chlorine will be substituted with the corresponding carboxylic acid. And how it's happening? First, upon treatment with this active magnesium, it will form this Grignard reagent, that is the organomagnesium reagent, and with this carbon dioxide, which is C double bond O and double bond O. In this, like this, upon treatment with this carbon dioxide, we will get this carboxylic acid. That is, this center over here will be negatively charged because magnesium is an electropositive element. So whatever negatively charged carbanion is there or negatively charged carbon is there, that will attack on this carbon of this carbon dioxide, and one of the oxygen will get polarized to form the corresponding carboxylic acid. So first step will be the formation of Grignard reagent, then attack over the carboxylic acid, then hydrolysis will give us the corresponding product. Is this okay? Moving to the next question, predict the major product of the following reaction. That is, this particular nitrile compound, upon treatment with this phenyl magnesium bromide and in second step with hydrolysis, out of this four options given here, which will be the major product? So here basically what is happening is that this phenyl magnesium bromide will be attacking over this nitrile group. So here pH will be coming, and here double bond NH, that is first intermediate whatever is forming is this option B. But since we are hydrolyzing that also, we will be getting this particular compound, that is whatever this ketamine is forming in the first step, that will get hydrolyzed to form the corresponding ketone. So the correct answer is option A. So it is going like this. So this is basically phenyl magnesium bromide, which will add upon this nitrile compound to get this intermediate first, and which can form this ketamine in the presence of any acid or during workup. Then again, when we are hydrolyzing this, it will be converted into this corresponding ketone. So this is not a stable compound. It is very susceptible upon catching moisture or hydrolyzing condition to convert into this ketone. So this is also a basic reaction of this organomagnesium reagent. So first this phenyl group will add on to this carbon, then this bond will shift to here, and that will form NMGBr, and then that will be converted into this ketamine, and then upon hydrolysis this double bond NH will be converted into double bond O. Moving to the next question. The product of the reaction, so this benzopyramide we are treating with methyl magnesium bromide in the first step, and in the second step with HCl and water, which will be the major product. This kind of benzopyramide basically we are using for this 1,2 addition on a ketone, because this is a very good leaving group. So here the correct answer is option B. So what is basically happening is that this from this methyl magnesium bromide, this methyl group will be negatively polarized and this magnesium will be positively polarized. So this negatively polarized carbon of this methyl group will attack over this ketone carbonyl carbon center to give this particular intermediate. So methyl magnesium bromide will be attacking of this carbonyl carbon center to give this intermediate. Then upon hydrolysis, what in the presence of acid, what is happening is this OMGBr will be converted into alcohol, and when this hydrogen will shift to here, this will leave and we will get this ketone. That is, in the presence of acid, what is happening is this will be converted into alcohol, and this nitrogen will also get protonated to form this positively charged species on this nitrogen as well. So this proton transfer is basically happening from this alcohol to this nitrogen, and this will be existing in the ketone form. So directly we can say this methyl group is attacking over here, and upon hydrolysis this group is leaving. So we will get this as the major product. Moving to the next question. Predict the major product of the following reaction. So here, this methyl lithium, we are adding over this compound that is basically an aldehyde. But here, what we have to see is the stereochemistry. Anyway, here it is 1 to addition is happening. That is, this methyl group is adding over this carbonyl carbon of this aldehyde. So we can expect option A or B. Mm, yeah, option A or B will be the, out of this option A or B, which will be the correct answer, because anyway here we have dimethyl substitution that is not possible with methyl lithium because already one proton is there with carbon. So over the aldehyde, one methyl group is only attacking, so these two options we can exclude. So out of these two options, which will be the major product? So here we have to see whether the methyl group, incoming methyl group, will be coming from the alpha phase or beta phase, and what is the factor that controlling that. So here the correct answer is option A. And now we have to see how it is happening. So what is happening is that just methyl addition over this aldehyde. So it can form both this anti-product as well as syn product, which are diastereomers, because this chiral center is already fixed in the starting material and only this chiral center is being generated. So this anti-isomer is forming in 91 percentage and this syn isomer is forming in 9 percentage. So why this is major is, the reason is that when we consider this Felkinen model, that is this aldehyde, that is ketone, we this carbonyl group we have represented here, then the proton here, and then the other carbon, which is this one. So that is like methyl group coming here, then H over here, and this amino group over here. So here what is happening is that this, since attack over this less substituted hydrogen side will be more easier, that will be the major product. That is methyl group will be coming from the same side as of this hydrogen. So in the starting material we know this hydrogen is already here, and this hydrogen is shown as above, that is beta. So the incoming methyl group will be also coming from the beta phase, but here in the answer it is shown as like in plane. So what we have to do is just rotate the carbon and then we can see that will correspond to this particular option. Or one more thing what we can do is just draw the answer in this model, that is this hydrogen and the incoming methyl group having the same stereochemistry, that is methyl group will be above and OH will be below, then hydrogen will be in plane. So that stereo center will be having the same configuration as what is given in this compound, and it will be having opposite configuration at this center for this compound. Like that also we can conclude out of the options which is the major product. If we are not like we are predicting a product and in the options the product is not given in the same format, that is one thing we can do. That is, first draw the Felkinen model, then methyl group will be attacking from the smaller group side, or we can say the less hindered position, which is from the hydrogen phase. That is, hydrogen is here beta, so the incoming methyl group will also be beta. So the this bond will shift to here and the OH will go alpha. So here that will be, I think, R sender will be generated corresponding to that. So if we see here, we can see this is also R, but this is S sender. So this is the correct answer. I hope it's clear. Moving to the next question. So this is also a similar question, but not the exactly same. The major product of the following reaction, that is, over this ketone, this butyl magnesium bromide is being added. So here also 1 2 addition is taking place. So out of this four options, we can directly cancel out option A and option B. Then out of this option C and D, which stereochemistry will be correct? So this chiral center is already generated, and these two are the possible diastereomers of the product, which will be the major product. Okay, sorry for that. So here the correct answer is option C. So here what is happening is that since there is already a heteroatom present here, heteroatom present here, that is this O mom group. Here what will happen is that it can undergo chelation. That is, so here I have already added that. So addition of Grignard reagent to chiral aldehyde or ketone can be stereoselective for the CRAM or chelation control product. So when a heteroatom is present, which is already present here in the O mom group, the chelation often dominates. So what is happening here is that through this particular model it is happening, and that is, this magnesium can coordinate with this oxygen as well as this oxygen. So through that side anyway the incoming nucleophile cannot come, and this side is already hindered position. So it will be again coming from the small group side. So the butyl group will be coming from the same position as that of the hydrogen. Small group, that is from the small group side it will be coming, that is the incoming nucleophile. So we will be getting this as a major product. So here I have given that when a heteroatom is present at the carbon atom, then chelation often dominates, and addition to alkoxy ketones gives the cyclic chelate represented by the Newman projection, and therefore favors the formation of chelation control product alcohol A. So through this side, this butyl group will be attacking, and we will be getting this as a major product. Similar to what we have explained earlier in the organolithium compound case, but here one difference is that since a heteroatom is there in the adjacent carbon, there is a possibility of chelation with this magnesium. So these are two major topics while we deal with the organometallic reagents, that is stereochemistry of 1 to addition. Particularly if a chiral center is already present adjacent to that ketone or aldehyde. Moving to the next question, predict the major product of the following reaction. That is, this particular compound, first we are treating with this phenyl magnesium bromide, then in presence of carbon dioxide and then followed by hydrolysis, which will be the major product. So here the correct answer is option C. So what is happening here is that first this phenyl magnesium bromide, this nitrogen is already having this lone pair. So this positively charged magnesium nitrogen will attack over this positively charged magnesium, that will form this particular Grignard reagent. And then this nitrogen lone pair will fall over here, and this carbon will attack over this carbon of this carbon dioxide, and it will form this particular 2 pyrrole 2 substituted carboxylic acid. So this is also an example for the reaction of organomagnesium reagents. So first what is happening is that this nitrogen lone pair will attack over the positively charged magnesium to form this Grignard reagent. Then this will again attack over this carbon, and that bond will shift towards oxygen to get this like carboxylic acid. Moving to the last question of this particular topic, predict the major product of the following reaction. That is, here one hydroxyl group is there, and here carboxylic acid is there, and we are treating with ethyl lithium and then hydrolysis. So out of this four, which will be the major product? So here the correct answer is option D. So this also we have seen professor have discussed in the lecture videos. So here what is happening? First, when we add this ethyl lithium over this alcohol and this carboxylic acid, both will be getting lithiated. That is, over here also it will get lithiated, and over here also this will be getting lithiated to form this particular compound. Then, in the presence of the next molecule of this ethyl lithium, which will add over this carbonyl carbon center, that will be forming this particular intermediate. That is, ethyl group will attack over here, and this bond will shift to here, which will form this O lithium species. Then, upon in the presence of acid or hydrolysis, we can say what is happening. This OLI will be converted into OH, and here also this will be OH, and this will be OH2 plus. And then this elimination, or we can say first all will be in OH form, and then one molecule of water will be eliminated to form this ketone. So the correct answer will be option D. So what is happening is that first ethyl lithium will generate this dilithium species, and then again next molecule of ethyl lithium will add upon to this ketone to form this particular compound. Then upon hydrolysis, one molecule of water will be eliminated to form this ketone. So that much questions I have added from this organometallic reagent part. So I hope it's clear what are the main features of this Grignard and organolithium reagents, how to prepare that, what are the various reactions of that organolithium species and organomagnesium compounds, how to determine the stereochemistry of these reactions if it is getting added to chiral compounds. Then we have seen some examples involving organomagnesium reagents as well as organolithium species. So now we will be moving on to the discussion on week 2 assignment questions. Already the due date is over, so now we can discuss that. And if you have any questions or doubts in whatever I have discussed in this organo metallic reagent part, you can ask, or else we will move to the week 2 assignment questions discussion. So here is the first question. The major product of the reaction, this particular alpha beta, like this active methylene compound with ketone at one position and this ester at other position, and we have this alkene in presence of NaH and butyl lithium, then hydrolysis, which will be the major product. So you can also try to answer this. Whoever is here, Sharmil, Manisha. So this kind of reactions we have already discussed in week 1 and week 2 tutorial sessions. So what is happening here is that first NaH will create this particular enolate, because proton being acidic, that enolate will be generated, and which will be in resonance stabilized with this particular enolate, that is over this ester or over this ketone. Then what is happening is that in presence of butyl lithium, that will abstract proton from this hydrogen over here, this methyl group, which is also acidic. So when the proton is subtracted from here, that bond will shift to here, and again this bond will shift to here. So that will result in this particular intermediate. And then what is happening is that this double bond can add over this position, and this bromine will be eliminated to give this intermediate. And then upon hydrolysis we will be getting this product. So this is an example for regioselective alkylation of active methylene compound. So the correct answer is option B. So first, this enolate will be forming, which will be in resonance form with this particular enolate, and upon butyl lithium, so first NaH will be taking the most acidic proton, that is this proton. So it can form either of this two enolate, which will be in equilibrium with each other. And then when we are adding the next base, that is butyl lithium, the next acidic proton is here, that is from this methyl group, that proton is being abstracted. So the negative charge will be formed here, that will shift over here, and this bond will shift to here. So this will be O minus, and this is already O minus here, and this that both O minus will be coordinating with the lithium. And then what is happening is that upon addition of this our second compound, this double bond will add up to this position, and this bromide will be leaving. So we will be getting this particular intermediate.
Ma'am, I have a doubt.
Hello.
Sodium. Hello.
Hello. Yes, tell me.
I have a doubt that
Yeah.
in sodium hydride,
Yeah.
hydride minus can attack that. But H minus after abstracting the methylene hydrogen atom,
No.
it can also resonate with the ester group and also the keto group.
Yeah, this one, right? This two.
So,
I didn't get your question. Can you repeat once?
there after abstracting
Yeah.
the methylene hydrogen atom, that minus charge get delocalized over the ketone and also ester group.
Yeah, either it can delocalize over this ketone, which will result in this, or it can delocalize over this ester, which will result in this.
Uh,
Okay.
So in butyl lithium, in case of butyl lithium, there may be difficulties to abstract the alpha hydrogen atom.
Alpha hydrogen atom, but there is one possibility is that these two are existing in equilibrium always. So whenever it is existing in this form, there is high chance of abstracting this proton by this butyl lithium, because this is very acidic when it is ketone. Okay, so
Thank you, ma'am.
this is not like this is existing only in this form or this form. It is not like that. It is in equilibrium. So this once formed, it can convert back into this, and this can convert back into this. So once it is in this form, the proton will be abstracted by the butyl lithium from this methyl group. Is it clear?
Yes.
Okay. So we will get this option as the correct answer. That is option B. Now moving to the next question, the major product of the reaction. So we are treating this compound, that is with one position nitro group and with one position bromine with K2CO3 in benzene, which will be the major product. So here, which one will be the acidic proton?
Acidic proton adjacent to the nitro group.
Yes. So what will happen first? This proton abstraction will take place to form negative charge over here, and then that will be attacking at
Then,
this position. Yeah.
then it will go to the carbon atom which is attached to the bromine.
Yes. And bromine will
Then it
knock.
form a ring.
Yeah. So this will be the correct answer, right? So one, two, three, four, five. Five-membered ring will be forming with nitro group. This anion will be generated, which will attack over here, and bromide will be leaving. So this will be the correct answer. Now moving to the next question. The major product of the reaction. This is an acid catalyzed reaction. So we are treating this alkene with HBr.
Second one,
Yes. So how it's happening? First, this allylic cation is forming when this will take up this proton, and this allylic cation is forming. Then whatever remaining Br minus will be attacking over this, and that is the nucleophilic attack by bromide ion will be taking place at the less hindered position. That will result in this product. So first, this allylic cation, whatever is forming, this bond will shift to here, and then this bromide is attacking over that cation. Now the next question, the major product of the reaction. So here again we are using this active methylene compound with one side ketone and one side ester, and we are treating it with this sodium methoxide and methyl iodide. So which will be the answer?
First one.
First one is the answer. So it is pretty clear, right? Proton abstraction is taking place from this position, and that negatively charged carbanion will attack over this methyl group, and I minus will be leaving. Through this phenolate, it is happening. Then the next one, the major product of the reaction. So this here also one ketone is there, here also one ketone is there in presence of KOH, which will be the major product, which will be the product.
First one.
First one or third one, where the
Third
double
one.
bond will be. So whatever your approach is correct, first proton abstraction is taking place from here rather than here, because six-membered ring will be favored over four-membered ring. So then what is happening is that the phenolate will be forming, and this bond will attack over this carbonyl center. This will be forming. So then which double bond will be formed? Like proton will
Uh,
be taken,
dot CID from dot CID.
yeah, from this center only, proton will be leaving. Because it is adjacent to ketone means that is also again acidic proton, so there is a larger tendency for it to get eliminated, so it will go with this hydroxide ion to form this compound. So option C is the correct answer. Now moving to the next question, the major product of the reaction. So here we are treating this particular compound with this methyl COCl, first with LDA, then with water and ethanol. Which will be the answer?
Second one.
Second. Yes, second one is the correct answer. So here what is happening is that first in the presence of LDA, this will add upon to this position, alpha position of this lactone, and that will form this compound. Then water ethanol will be deprotecting this Cl group, which will form this compound. So this is an example for base catalyzed acylation reaction. First, this negative charge will attack over this carbon and the Cl minus will be leaving in the presence of LDA. Then water ethanol will deprotect this TBS group to get this option B. Now the next question, the major product of the reaction. So this particular compound is treated with NaH, two equivalents and excess of methyl iodide, and then H2SO4.
Fast
Yes. So what is happening here? So we, since we are using two equivalents of NaH and two methyl iodide, both the acidic protons which is near to the nitrile group will be abstracted, and then in presence of H2SO4, that nitrile will be converted into carboxylic acid. Now the next question, the major product of the reaction. So here also we are treating this carboxylic acid with this benzyl bromide in presence of butyl lithium, followed by acidic workup, which will be the product.
fourth one.
Fourth one, yes. So that acidic proton which is adjacent to this carboxylic acid will be abstracted by butyl lithium to form this compound. That is, this enolate will be existing as this lithiated species. Then this will attack over this position and Br minus will be eliminated to give this option D. Moving to the ninth question. So this compound in presence of K2CO3 and ethanol, which proton will be acidic here? Which will be the correct answer? So here first proton abstraction will be taking from here, right? So proton abstraction will take place from here, and that will be attacking over this. So that will be basically resulting in a 5 XO ring closure, we can say. Yes. So this whatever negative charge is forming here, that is attacking over here. 1 for addition is taking place, and then this will be converting to enolate, and that will give this option A. Is it fine? And since it is 5-5 fused ring, mostly this is confirmation will be mostly preferred over trans. So negative charge will be forming here, and that will undergo 1 for addition to get this 5-5 fused ring in cis fashion. Now the last question, the major product of the reaction. So this compound upon treatment with LDA in THF at minus 78 degrees Celsius, followed by LiBH4 and then Amperlist 15, which will be the major product.
Here, amber list 15 is a resin.
Yeah, it is acidic resin. So like what we do, we are adding catalytic amount of HCl, H2SO4. So same purpose only Amperlist only will be do. It's also acidic in nature.
It is acidic.
Yeah, acidic resin. Amber list, then we can say amber light 120H plus, then Dovex 50. All these are acidic resins. Which will be the answer? So correct answer is option B. So what's happening here is that, sorry, yeah. So first LDA will abstract the proton which is adjacent to that ester group, and that will attack over the double bond. That is the role of LDA. That is first step we will get that particular intermediate shown here. Then in the presence of LiBH4, that ester will be reduced to alcohol, like Yeah, that ester will be converted into CH2OH, and that alcohol will attack over that particular Weinreb given there, not Weinreb exactly. Yeah, that particular carbon of above position, and that will knock out that NME2 group, which will result in that option D. Is it clear? So, so first proton abstraction will take place from the alpha position of the ester group, then cyclization to form the cyclopentane ring, then ester reduction to get the alcohol, then that alcohol will attack over that amide, and that NME2 will be knocked out to form that lactone. So that was the last question of week 2 assignment. Yeah, so that's all for today. If you have any questions, you can ask, or else we will see in next week's session. Thank you for joining.